In this video, we're going to discuss the acid-base properties of water. We're going to start by writing the auto-ionization reaction for water. In this reaction, two water molecules react together, one acting as a base, one acting as an acid. The two water molecules react and form the hydronium ion and hydroxide. This is the auto-ionization reaction of water. Notice that water is a species that can act both as a Bronsted-Lowry acid and as a Bronsted-Lowry base, and is therefore amphoteric. Let's identify the conjugate acid and conjugate base of water in the reaction above. Notice that hydronium, H3+, is the conjugate acid of the water molecule acting as a base, and hydroxide is the conjugate base of the water molecule that's acting as an acid. Let's write the reaction quotient for this reaction. The reaction quotient is, as always, the concentration of the products over the reactants raised to their stoichiometric coefficients. Both of the reactants in this reaction are pure liquids, and therefore they're not included in the reaction quotient. So the reaction quotient for this reaction is simply the concentration of hydronium times the concentration of hydroxide. At 25 degrees Celsius in neutral water, the concentration of hydroxide and the concentration of hydronium are equal to each other, and they both equal 1 times 10 to the negative 7th molar. Because the concentration of hydroxide and the concentration of hydronium are both known for pure water at 25 degrees Celsius, we can plug those values into our reaction quotient and calculate the equilibrium constant for water. We call this Kw because it's a special equilibrium constant that we'll use often in this course. Kw is the product of the hydronium concentration and the hydroxide concentration, and it always equals 1.01 times 10 to the negative 14th. Let's do an example calculation. Let's say we have an aqueous solution with a hydronium concentration of 2.0 times 10 to the negative 9th molar. What is the concentration of hydroxide in the solution? To calculate the concentration of hydroxide in the solution, we set Kw equal to the concentration of the hydronium times the hydroxide, solve for the hydroxide, and then plug in our known values of Kw and the given value of the concentration of hydronium in the solution. We then calculate that the concentration of hydroxide in this solution is 5.0 times 10 to the negative 6 molar.